Hello. So in the previous video, we learned about Green's functions. So in this video, we are going to solve a problem based on the Dirichlet boundary conditions and our condition will be something called a planar boundary condition. So for any Dirichlet problem, as discussed in the previous video, we must define a surface. So let this be our surface and a volume V. So this surface is specifically the surface z equal to 0, and this volume is all points with z greater than 0. So for a Dirichlet problem, we must define the charge density in the volume V and the potential on the surface S. So the charge density on the volume V is simply defined by a point charge Q located at a point R1, and this point is simply, let's say, 0, 0, Z0. So our charge density in V is simply a delta function. Now we need to define the potential on the surfaces. Let's say that the potential for R on S is 0. Alright, so basically phi of xyz for z equal to 0 is 0. These two are the same statements. Alright. So now we have defined our problem, and like all Dirichlet problems, we need to find the potential for R in V. That is xyz, where z is greater than 0. So let me define another problem which we will soon see is actually equivalent to this problem. We have the same surface S, which is at z equal to 0. This region is z greater than 0, and we have a point charge Q, and that is also located at a point R1, which is the same point. Now I also place another charge which is opposite in magnitude, and I place it at a point which is called the image point of R1, which means it is the reflection of this charge with respect to the surface S, or we can call it image of Q with respect to S. And this charge is also called an image charge. Now let us see what is the potential at any point on the surface. So by simple geometry, we can see that the charges are equidistant from any point on the surface. Let us say this distance is d. Then the potential at this point is given by phi equals, we know that the potential at a point due to a point charge is given by q by 4 pi epsilon naught, and the distance between the charge and the point. And similarly, here we will have minus q and the same distance t, because both the charges are equidistant from the surface. This is because of the mirror symmetry. And we see that this is 0. So in both the cases, the potential on the surface is 0. Alright? So this is equivalent to this. Hence, these two problems are similar because they have the same charge density in the volume V. As you can see, here also the charge density is the same due to one single point charge at the same position. We also have the same boundary condition, because in both the cases the potential at z equal to 0 is 0. So by the uniqueness theorem, the potential at any point in V is same for both the problems. And what is the potential for this problem? Here we have q, here we have minus q, and this is at R1, this is at Ri. So the potential at any point is simply given by this arbitrary point is R, so it is given by R pi of R is q by 4 pi epsilon naught, and we have a distance function R minus R1, and here is a minus sign. This is simply the potential due to a point charge R minus Ri, where we must define, okay, let's simplify this. Q by 4 pi epsilon naught 1 by R minus R1 minus 1 by R minus Ri, where we must define that in the Cartesian coordinate system, R can be any arbitrary point x, y, z, where z has to be greater than 0. This is due to the problem. R1 is the location of the point charge here, which is 0, 0, z0, and Ri is the point which is the image of the point R1 with respect to the surface z equal to 0, which is simply 0, 0 minus z0. So we have solved our problem of the Dirichlet boundary condition by converting into an alternate problem with the similar charge density and boundary condition, which is much easier to solve, and we have finally just solved our problem. So this method of solving is called the method of images for obvious reasons. Now, let's try to generalize this problem. What will be the generalization of the problem? Let's say we have our surface and This is any general surface and the volume is on one side of the surface. Alright. Now this is a planar surface, of course. Any general planar surface. And the charge density on one side of the surface is given. This can be any general charge density. And we need to find the potential in V. Alright. So by our previous problem, we can find an image charge equivalent to the charge density. But let us try using the Green's function. So using Green's functions, we know the solution of the Dirichlet problem is given by this integral. We have our charge density, we have the Green's function, and we have a surface integral. Where we have the potential and the gradient of the Green's function. Alright, so for this problem we need to find the Green's function, which for the Dirichlet problem must satisfy this condition, that it vanishes on the surface and that its Laplacian is this. Alright. Now, and of course, let's say the potential on the surface is given, because in the Dirichlet condition the potential on the surface has to be given. So this can be any general potential. Let's say the potential is given as, let's say it's a constant, which is the case of a conductor. Doesn't really matter whether it's a constant or a function of r, we just need to substitute it here. For example, in this case, this is simply phi naught. So what should be our Green's function? Now we take inspiration from our previous problem, where we had found out that the potential, let's now call this potential as phi p, indicating this is our previous problem. Potential we found out as q by 4 pi epsilon naught 1 by r minus r1 minus 1 by r minus ri. Alright, and this potential was 0 for r on S. Now our Green's function has to be 0 for r dash on S. So a very logical transformation would be to take r to some r dash. Now trust me on this, and let's take r1 to r and ri to, let's not change the notation here, but by definition ri here should be the image of r. Of course, we always take the image with respect to the surface S. So specifically, if r is given by x, y, z, then ri, in our case the surface is z equal to 0, So it will be given by xy minus z. This is just an example. However, for any random surfaces, this image point may have some different form, but it is definitely the image of R with respect to the surface. So for our general case, just this definition suffices. Alright, and we define our Green's function like this. R dash minus R minus 1 by R prime minus R. So this Green's function is definitely 0 on the surface because this potential is 0. It is simply by the method we got the Green's function from the potential. Now all that is left to show is what is its Laplacian. So for this, we actually need to know the following results, that the gradient of the inverse distance function is simply given by this changes sign, this function. Now you can prove this. There is no physics in this, it's simply mathematics. But you can prove this. One way of proving this that I know is using Cartesian coordinates. And simply using the definition of gradient over there, which is uh, the sum of the vector derivatives or with respect to the coordinates or something. But in our case, we can simply use these as results, and from here we can get the Laplacian is simply minus 4 pi delta r minus r prime. So you can already see the reason why we have taken our Green's function in this form, because now if we take its Laplacian, it will simply come out to be minus 4 pi delta r minus r prime, and this will be 4 pi delta ri minus r prime. And if you notice by the problem, this r prime can never be equal to ri. Why is it so? Because by definition, this r prime is always in this volume V, and ri is always outside the volume V, as it is the reflection of r with respect to the surface. So it has to be outside the volume V, and r prime is inside the volume V. So for the purpose of these integrals, which is what gives our solution, so these integrals are important. So for the purpose of these integrals, the r prime is in V or on the surface S. In both the cases, this holds. Hence, this delta function always vanishes. Thus, we get the desired Laplacian. Hence, this Green's function works. So, we get the final answer by substituting this Green's function in our potential, and we have now one may further simplify this gradient by using the result for the gradient of the inverse distance function, and depending on what our charge density is, we can solve these integrals. However, we will leave the answer in this integral form only, and this will be our general solution for the planar Dirichlet problem, where we have again some planar conductor, and we need to find the charge density on one side of the conductor is given, and we need to find the potential in this region, and we solve this by using Green's functions. And how did we arrive at the Green's function? By generalizing an image problem.